right, so we have one last talk, and I think this talk is very interesting for both ways. One way is that it really tries to look at the FE2IO transformation and tries to do something that is different from the very inefficient GGM, which is a great challenge. And the next is a couple of you were wondering about whether anything is implementable, and actually Sora is going to talk about the implementation benchmark. So you will have your answer whether it runs under an hour or it runs under a day. So
yeah, thank you.
Let Sora start.
Yes, okay. Hi, everyone. Yeah, so I'm Sora from Machina IO project within Ethereum Foundation. So we are working on IO with the goal of building practical IO. So today, I'd like to talk about Diamond IO, the lattice-based IO construction we proposed. So yeah, I think this is a maybe sad talk about the new lattice IO construction today. Yeah, but our first slide is not the definition of IO. So over decades, researchers have been climbing a mountain called IO, and then many of the recent constructions built a cryptographic primitive called functional encryption. So this is a generalization of the public key encryption such that a secret key is associated with the circuit, and the decryption process outputs the circuit evaluation result on the plain text and the ciphertext. And many schemes have used this because they learn known bootstrapping technique from functional encryption to IO. However, when we try to implement IO, this becomes one of the biggest bottleneck because this requires recursive FE encryption. Specifically, this requires running the FE encryption algorithms within the circuit evaluated during the decryption process. So we address this problem by replacing the recursive FE encryption with simple matrix operations. So more concretely, we achieve that by adapting the idea of the FE scheme introduced in our AK-124 in a non-black box manner. And then we prove the security and the sub-exponential security of the LWE evasive LWE along with our new assumption called all product LWE. And this is also in the pseudorandom oracle model. And we implemented the diamond IO construction with some limitation and the simplification. So this is not yet the perfect construction, but it includes our novel technique, which replaces the recursive FE encryption. And we will share its benchmark result. OK, so this is the outline of today's talk. And first, I'll talk about the core ideas behind the diamond IO construction. So in short, so the point is that this is a combination of GGH15 encoding and the BZZ plus encodings to make a straightforward construction. So our first idea was inspired from the AK-124 FE scheme. So this makes a lattice-based encoding called BZZ plus encoding, which encodes the FEG encryption of the private input. And our first idea was that if we have some way such that evaluator can insert inputs or evaluator's input bits into the encoding which provided by the obfuscator and which encodes the encryption of some private circuit being obfuscated, then we can take the similar approach to the FE decryption or in this AK-124. And this might provide a new path to construct IO without the recursive FE process. And before taking a deep dive into this, so we focused on building this step. And before taking a deep dive into this, we first introduce some preliminaries, but this is just in 3 slides. So first, we technically construct a pseudorandom obfuscation first. So this is, as introduced in today's talk, this is our obfuscation, IO, for pseudorandom functionalities. And in the paper of this BDJ plus 24, so this paper show that in the pseudorandom oracle model, pseudorandom obfuscation can be easily transformed into I/O for general circuits just by computing the hash function as a pseudorandom oracle within and outside the obfuscated circuit. So since this does not make a large overhead, if we can compute hash function, we follow this approach so that in the following, we only target pseudorandom functions. And the next one is our BZZ press encoding. So this is like there are some notations, but we define the BZZ press encoding in this way, where this S is a secret vector, and this A is a public matrix, which is independent of the actual inputs XY to XL. And this satisfies, this enables, so we can compute addition and multiplication of the encodings homomorphically so that anyone can compute the encoding corresponding to the circuit output. And notably, this SE is deterministically derived only from the input public matrix and the circuit C, so that this is independent of X and CX. And the one limitation of the BZZ press encoding is that this cannot natively handle private data because its homomorphic multiplication requires one input of the multiplication need to be public. And many previous works overcame this limitation by encoding the FEG encryption of some private data, and sometimes with the encodes secret key, and performs the FEG evaluation and the decryption processes on the BZZ press encoding by describing such process as a circuit. And by doing so, anywhere evaluator can obtain the BZZ press encoding, which masks the decryption result by the first term, S times AF. And since this AF only depends on the AF is specific to some circuit evaluation, if the trusted party reviews this first mask data to produce this first mask, but only for some permitted circuit, then this evaluator can obtain this decryption result non-interactively. And in the AKY24 FE scheme, this F is concretely defined in this way. So the highest bit of the output contains the circuit evaluation result in the plain text. And the lower bits contains the PLF output plus some LW errors, so that even if some noisy decryption result with some error is revealed to the evaluator, this does not break the security, as they are masked by the PLF output. And we go back to our construction. So our first attempt, inspired from AK124, is that, as I described, if obfuscator provides the BZZ press encoding, which contains the FEG encryption of the circuit and the PLF key K, and if evaluator can encode their input bits to the given encoding in some way, then we can take the similar approach to obtain the decryption result by using another data provided obfuscator, which generates the first mask of the decryption output encoding. So then the remaining question is how to achieve this process. And we consider this problem backward from the goal. So let's say, for example, we have two input bits, and the evaluator can generate the input encodings for every input pattern like this one. And we can consider two cases. So first case is that the public matrices in these resulting encodings depends on each input bit. In this case, we have an efficiency issue because this AF depends on each of the public matrix, so that obfuscated circuits size grows exponentially to include all of the data to generate S times AF for every public matrix patterns. And if these A matrices are independent of input bits, then we have a security issue because by subtracting the by computing the difference between two encodings with different input bits, evaluator can easily cancel out this S times A so that they can recover S from the S times gadget matrix. So we solve this problem by embedding the input dependency into the secret key rather than public matrix. So concretely, we define the input-dependent secret key as the product of the secret matrices, each of which is defined for each input slot and the input bit, like this one. And by doing so, we can first see that public matrix is independent of the input bits, so we can solve the efficiency issue. And also, since secret key will be different, adversely cannot trivially cancel out the first term S times A in the similar way. However, this does not mean this construction is secure. So this is why we still need the new assumption or product LW to discuss the pseudorandomness with such input-dependent secret key. So the next question is that then how the evaluator can generate such BZZ plus encodings for every input patterns, which has potentially 2 power of L patterns only from the polynomial-sized circuits. And yeah, this seems to be very difficult, but we can solve this by combining the GGH plus 15 encodings, GGH 15 encodings. So in these encodings, a trusted party prepares 2 power of L number of the play images like this one. Then, and here, this K denotes, this notation means play image K is sampled for the target matrix A. And this satisfies B times K equal A. And this sampling process requires the knowledge of the trapdoor for the public matrix B, so that only the trusted party who can generate such play images. And the untrusted evaluator can produce 2 power of L patterns of the GGH 15 encodings by changing how they multiply each preimages. So similarly, in our diamond IO, the obfuscator generates provides 2L number of the preimages, and each of the preimage contains a matrix, public matrix, to update the insert new input bits xi into the sequence of the encoded bits, along with the matrix corresponding to each input bit. Then evaluator, for example, if the evaluator's first input bit is 0, evaluator multiply this play image by the given initial GGH 15 encoding, so that they can update the insert x1 along with updating the secret key. And if the second input is x1, evaluator multiplies k21 to update the input bits and the secret key, and evaluator repeats this process until the last input bit, so that evaluator can obtain the GGH encoding, which contains all of the input bits and the secret key that depends on all of the evaluator's all input bits. And finally, obfuscator additionally provides a play image to combat this GGH 15 encoding into the BGG plus encoding, so that the evaluator can obtain the desired BGG plus encoding. And although this is for like a final decryption process, obfuscator also provides a play image to generate S times AF for every input-dependent secret keys. So in summary, the obfuscated circuit is defined in this way, and our data, vector matrix, and the play images in these yellow box are used by the evaluator to insert input bits to the given GGH plus encoding and generates its corresponding BGG plus encoding. And then we take the similar approach to recover the decryption result from this. evaluation result from this encoding. Okay, so this is the point of the, this is our core ideas of the construction. And we next go to the security analysis. So we rely on our private coin evasive adverbary to discuss, to analyze our security of the adverbary instances with plain images. And the evasive adverbary claims that if the precondition where our S times adverbary instance S times B and the multiplication product of this instance and the plain image S times P becomes like a pseudorandom, then the plain image does not break the pseudorandomness of this S times P in the post condition. So our security proof consists of two steps. So in the first step, we prove that the pseudorandomness in the play condition using the adverbary and our new assumption, all product adverbary. And in the post condition, we prove the pseudorandomness of this obfuscated circuit by applying the evasive adverbary step by step. And recently, like two papers, HAL 25 and MY plus 25, proposed an attacks against evasive adverbary with the sampler definition used in this AK124 FE scheme. And this is also effective in our original construction. However, we can recover construction from these attacks either by involving the rounding as in the same way as the method introduced in the updated construction of this AK124 FE scheme, or just by fixing the horrific or PLF construction to honestly designed one, because this attack depends on the contribute designed or construction of the horrific PLF evaluation. So while we take the first approach in the theoretical construction, we will take the second approach when we implement this PLF in a secure way. So however, we also depend on the new assumption or product adverbary. So intuitively, this claims that our exponential number of the BZZ plus encodings, the joint distributions of this exponential number of BZZ plus encodings and the adverbary instances remain pseudorandom, and each of which depends on different secret key, input-dependent secret key we defined here, and also our independently sampled Gaussian errors is added to each instance. And so we find that if we remove this CA part, which corresponds to BGG plus encoding from this joint distribution, we can prove this assumption based on adverbary in this way by repeating such reduction for each secret matrix. However, when we include this CA part, this does not work because even if we try to replace this A minus XLG path with some uniformly random matrix provided by the adverbary challenger, this does not simulate the exact distribution, since while in the real distribution, this A minus XLG between two input bits have some relation such that this A can be canceled out between each other. If we simulate A in this way, this subtraction still be a random matrix, which is not same as a real case. So this approach does not work, and this is why we still cannot reduce this assumption cannot reduce to the adverbary. So some opening questions in terms of security is that first, so can we replace this evasive adverbary in its applications, including AK124 FE scheme, with another adverbary with hint assumptions, while preserving the simplicity of the original construction? If we can do that, I expect we can also replace the evasive debris with more robust assumptions. And also, second point is, can our product debris reduced to other lattice assumptions that could be stronger than debris, but still falsifiable, such as tensor debris or synced debris? Yeah, so finally, I present the benchmark results. Okay, so yeah, this is our our implementation of this diamond IO, and this is completely open sourced. Maybe this is very rare to share the GitHub repository in this obfuscation workshop. Yeah, so however, it's still not the perfect implementation. So especially, yeah, like it has some limitation, and also after we measure the benchmark, we found the initial PLF construction designed only for implementation cannot be proven secure based on the assumption we already rely on. Yeah, we are currently fixing this path and trying to remove these limitations while keeping the efficiency. However, the current construction already implements the input insertion technique we propose, so that we can at least say the input insertion process, which replaces recursive FE encryption, is ready for the implementation. And this is a benchmark result. So here we compare the various execution times and the data size according to with changing the input size to the obfuscated circuit.
MIN stands for milli nanoseconds.
Sorry?
MIN is milli nanoseconds.
Unfortunately, no. So how do you think? Yeah, it's a minute. So for example, even for input size 4, the obfuscation takes around 5 hours, and the size of the obfuscated program is around 65 gigabytes. Yeah, and however, when we see the evaluation time, while it takes 49 minutes for loading the obfuscated circuit from the disk to the memory, after that, its evaluation time just takes 18 minutes. So if we have enough resources such that obfuscated circuit can be loaded, entire obfuscated circuit can be loaded into the memory beforehand, then I think its running online, running time can be just 8.
Machine did you implement 294 gigabytes of memory is quite large. Right?
Yeah. So we use a super strong AWS machine.
500 gigabytes.
Yeah.
I4I.
Yeah. 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 So this is the current progress of the.
If you want discounts on AWS, talk to me.
Yeah. Thank you. Great. Yeah. So the size is so.
To the end circuit or no?
Sorry.
So what's the size of the circuit before obfuscation?
Yeah. So the original circuit is the circuit evaluated on BZZ plus encoding has, I think, 3 multiplicative dips, but the number of gate is let me check the. Yeah, this is a spec of the circuit we evaluated. So so it's also add more gets than application specific one, because we have, for example, get for FEG decryption and so on. Yeah, so so this is the number of the gates evaluated over BZZ plus encoding. So if we implement this as the same way as the theoretical construction, we further have overhead to simulate FEG evaluation on BZZ. However, I don't think this is a correct approach in terms of the efficiency. So so this is a roadmap to practical IO. So if we can support the FEG decryption and the snag verification within the obfuscated circuit, then we can scale the like a size of the obfuscation more easily because as proposed in GGH plus SAT13, because we can use IO only for the conditional FEG decryption, and we can do the application-specific computation within FEG. And however, to do that, we first need to support more larger input size, especially for inputting the ZK proofs. And however, yeah, it takes already like 65 gigabytes only for 4 input bits. And the main reason is that the modulus Q increases exponentially with respect to the input size due to the multiplicative increase of the error for each prime-image multiplication. So our current idea is that if we can implement some noise reflection process during input insertion process in similar to FEG's bootstrapping, then we can bound the size of the modulus so that we will be able to support more larger input size. And this will require both the arithmetic operation and the nonlinear operation. So our current plan is to implement natively efficient lookup evaluation techniques over BZZ percent encodings. And if we can do that, we think we can implement both the noise refreshing and PLF computation easily. So our main concern in terms of efficiency is that how can we optimize the computation over BZZ percent encoding? And if we can replace just a bit Boolean simulation over BZZ with the native arithmetic operation over the modulus Q plus some lookup evaluation, then we can handle the super complex program circuit which involves both the arithmetic operation and the nonlinear operation. So this is our next approach towards the practical IO. We will continue our research both from the security and the efficiency perspectives. Yes, thank you for listening. Yeah.
So have you tried to compare your approach in terms of efficiency to this Crypto 17 paper with Dan Brunet, David, and Amit? We had a paper that exactly optimized the obfuscation of FEG decryption and smart verification. 5.
Yeah.
We used the multilinear map based.
Yeah.
The conclusion was that it's borderline implementable, not practical, but seems, on the face of it, potentially better. I don't know. I will try to compare it.
Yeah, I think we have not concretely compared them, but I think this is one of the earliest paper which tries to implement IO. Yeah, so we will carefully check the compare the results. Yeah, thank you.
Yeah. So, sorry. So my understanding is that you do BGG plus encoding over GGH 15, right?
Point is that it's not BZZ over GGH. So the point is we use GGH 15 encoding only for preparing the BZZ plus encoding, which contains imprints.
Right. Yeah. So what did you try to compare against just the GGH 15 IO candidate directly? So that gives you a heuristic constructor. That seems like a lighter weight.
So we have not compared the complete benchmark, but my intuitive assumption is that if we use GGH 50 encoding directly, we have to express the circuit as a matrix branching problem, so that length will increase exponentially, or we only handle NC1 diff circuit. So,
but even a 1-bit circuit or a 4-bit circuit, do you think that's going to cause a problem?
Yeah.
That's honestly, I can see.
Yeah, so.
For the small scales that you're considering.
Yeah, that's what's the last point?
But you're considering very small circuits right
now. So input size is very small, but actual number of the gates are evaluated on BZZ is our actual number is this one, because this also involves some linear operation to simulate FEG decryption, but we can still handle this. So
So which part is worse, the BGG part or the GGH part?
What's sorry? What's in terms of
Which part is more expensive? GGH part or the BGG part?
I think. I think in terms of their execution time, or the total time of the total time to insert all input bits can be is like to insert all input bits through the GGH50 encodings can be longer than the BGG percent encoding.
BGG is already pretty terrible because it's BGG over FHE, and then yes, GGH is even worse.
Yeah, and so this is also why our current implementation only supports linear homomorphic evaluation over BCC. Yeah, and like a more essential like a bottleneck is that so when we handle GGH, so the error accumulated error will increase in a multiplicative way because we multiply like a trap play image directly to the error, so that error will increase exponentially, and we have to ensure that mergers will grow more rapidly than this error goes. So like I think if we can bounce the modulus, then like this benchmark will be better. Does anyone have more questions?
Maybe can you say a little bit more what went wrong when you? I mean, you said that you found an attack.
Yes.
Can you say a little bit more against what?
Yeah. So attack is that the point of the this like a heuristic PLF construction designed for implementation, because in theoretical construction we assume like a PLF is computed over FEG over BCC, but this is like not straightforward. This is not easy in terms of the efficiency, and the first idea we had is that using the OR product, so we consider the like a LW like a rounding variant of this OR product LW, such that we assume the SXL times some like a public matrix like R of, and after so we define the PLF by like a SX rounding of the modular switching of the SXL times R, public matrix R, and if the difference of the modulus is sufficiently large, like we can take the similar proof technique to prove that this LWR is secure based on LW. So similarly, I expect we can say like such LWR is like as secure as the all product LW. But yeah, I think there are two problems. So first point is that so in this like a PLF, we need the PLF size, PLF, which is as large as Q over 4, so that like a difference between Q over 4 and Q will be like too small to ensure this like a security reduction from the rounding version of the OR product category to OR product category. And also, yeah, I think it's very simple mistake, but like so initially like we added the rounding of the public matrix to this like a target matrix in this KF frame image because like SX because like rounding of this S times A is like approximately close to the S times rounding of this like public matrix R, is similar to how modular switching of the LW works. But like this actually works only in the like a modulus P, where P is switched modulus, but we compute this in modulus Q. So like yeah, this does not make any kind of security reduction. So like yeah, our current plan is to implement the lookup evaluation over BCC in a more native way, and we compute the hash function over BCC publicly, and we use the weak BLF, like some inner product module switching of some LW secret times some like a hash of the like hashed public matrix as a PLF output.
Like some dark matter PRF? Or
Sorry?
Is it some dark matter PRF?
Dark
matter.
Dark matter.
Sorry.
It's like a more LWR based weak PLF.
Okay.
And we replace the input seed A with the hash of the input. And yeah, one good point is we can reuse this hash to like convert pseudorandom obfuscation into IO. Okay, thank you.